Hi, Adam.
Hello, Bob. How are you?
I cannot complain. Let me introduce us. I'm Robert Wright. This is The Wright Show, available on both streaming video and via audio podcast, as is, by the way, the larger meaningoflife.tv feed. There's a podcast feed for that. Not that you asked, but it's true. And you are Adam Frank, and a professor of, is it astrophysics at the University of Rochester, officially?
Yeah, astro. Yep.
And also an eloquent spokesperson for science. Did you found or co-found or something this NPR blog 13.7, where I've seen your work?
Yeah, we were Marcelo Gleiser and I co-founded. It's recently just ended, but it was 7 years. A good 7-year run, and we did a lot of interesting things.
Well, it's called 13.7, so I guess 7 was called 13.7. So 7 years makes perfect sense.
That's exactly right. So we just nipped out. And now, of course, we think that the universe is actually 13.8 billion years old. There's still a little debate about that, but new data sort of suggests. So that's why it was just time to get rid of it, right? You know, didn't make sense anymore. We had to move on.
You're going to start one called 13.8.
We are, actually.
And you've written a lot of stuff, including this book, which we're here to talk about, Light of the Stars, Alien Worlds and the Fate of the Earth, by you.
Bye.
And it's a really fascinating book, and it raises the question of why we haven't heard from these aliens in light of the growing reason to believe that they're out there, right? And there is growing reason to believe. And so there's kind of two questions here. What is the growing reason to believe they're out there? And if they're out there, why haven't we heard from them?
Right.
And the book spends a lot of time on why we are have more and more reason to believe they're out there. And do you think they're out there?
Yeah, and also, I do. Well, I think, so there's this work we did a few years ago that looked at what the Kepler data showed us about the number of habitable zone planets, and we can talk more about that. And so, I wanted to use that data to really also, because it's not just what we now have, we can think about exo-civilizations, as I like to call them, differently, but it also has relevance for climate change and what's happening to us now. So I think, not only should we be thinking about aliens or exo-civilizations differently because of everything that's been happening, but we should also start using that understanding to change how we frame our understanding of what's happening to us now.
Right. You early in the book you invoke Carl Sagan's teenager metaphor.
Right, and that's really the thing. Is that what's really interesting is actually to look at the history of the way people have thought about exo-civilizations and climate change, because it turns out they're really kind of coupled. 3 amazing things happened in the early 60s. The first was the first meeting ever on exo-civilizations. That was Frank Drake holding his very famous meeting where he came up with the Drake equation. They were it was just a small meeting where Carl Sagan and others with Frank Drake were trying to figure out how do you figure out how many aliens, how many civilizations there might be out there to talk to. And second thing that happened was in 1962, we sent the first interplanetary probe. America managed to get a probe over to Venus. So that was a big deal. That was the beginning, really, of our interplanetary age. And remarkably, Venus showed us something very important about climate change. It showed us, Venus is a scalding hell because of the runaway greenhouse effect. And then, just a few years after that, President Johnson gives a speech before Congress where it's amazing. This was so long ago.
That was amazing. When I came across that quote in your book, I was blown away. That's a way early allusion to climate change.
It was more than an illusion. He'd been briefed by people like Roger Revelle and all the guys who first recognized, the earth scientists who first recognized that CO2 was becoming a problem. So in 1965, he gives a speech before Congress where he says CO2 is going to be a problem. There's going to be climate change. And so that gives the real lie to people who are like, oh, climate change is this modern, hoax. People at the highest levels of power, people have been talking about climate change since 1965. So those 3 things were happening all at the same time, and it sort of shows you how this cultural jigsaw puzzle of our, emergence into space, becoming a spacefaring race, our thinking about alien or exo-civilizations, and our recognition of climate change were all sort of interwoven. And now, decades later, we've really crossed the Rubicon where we know climate change is happening. Our understanding of planets and of the possibilities of exo-civilizations has also just, completely been transformed. So I think they're all meant in some sense to happen at the same time.
Okay. Maybe I won't ask you what you meant by saying when you said they're all meant to happen at the same time. No, maybe I will. What do you mean by that?
Well, here's the thing. So the work, some of the work I'm talking about in the book is our own research looking at how any civilization. That's one of the premises of my book is A, there have been a lot of civilizations before us, most likely, and that B, most of them probably trigger climate change. It's going to be pretty hard if you're a world-girdling civilization to not trigger climate change. And the thing I think that's probably going to happen is your space age, a civilization's space age, and its climate triggering could probably happen in many places at the same time because you don't have the industry, the technology to get yourself out of the gravity well until pretty much you have the same kinds of technologies that are probably driving you into climate change at the same time. So and also you may not even recognize your climate change unless you can look down from above in orbit from your planet. So there may be a way that this sort of confluence of, getting out into space, triggering climate change, and also thinking about exo-civilizations may be kind of like, again, the cosmic teenager, right? Every time a teenager matures, there are things that are common about it. I think that these, that may be what's happening to us now. We are cosmic teenagers because all of these sort of maturation milestones are kind of happening to us at the same time.
Okay. And tell me if I'm being too apocalyptic in kind of trying to draw another kind of connection among these things. When you ask, well, if there are these alien civilizations out there, and we will get to the reason to believe that there may well be. Why haven't we heard from them? One answer you hear is, well, they didn't last very long, and climate change is among the apocalyptic scenarios, not the only one, and I think some of the others are possibly underrated. But I took, when the significance of the teenager metaphor, Carl Sagan saying we as kind of a species are just in our adolescence, to be suggesting, for one thing, that if we don't mature, our civilization could itself be short-lived, and if that's the norm out there, then maybe that explains why we haven't heard. So in that sense, in other words, the story frames our predicament.
Yeah, exactly. And I think that's probably, I think there's reasons to argue why that's true. The interesting thing about climate change let's introduce a new term, right? The great filter. So the idea of the great filter is that maybe we haven't heard from other civilizations because there's a filter, an evolutionary filter that keeps them from evolving. So it could be that the great filter is behind us in the sense that, in general, it's very hard just to make intelligence. So that there's just, in the universe, there's very few times that a planet evolves intelligence. But more worrisome is it could be ahead of us,
right.
In which case nuclear war, something stops many civilizations or most civilizations from getting past the point we are at. And in that sense, I think climate change is actually a very good candidate for the great filter because think about nuclear war, right? It used to be everybody worried about nuclear war, but nuclear war requires a certain kind of evolutionary psychology, right? You have to have, your evolutionary baggage has to be from a competitive species that does warfare. And you can imagine that there's lots of species that just don't do that. That's just, and especially something as radical as building an atomic weapon, you could imagine that a lot of species would be like, no way, that's crazy, I'm not doing that. Whereas climate change, you almost can't stop it. If you build a world-girdling civilization, it's just the impact of lots and lots of little choices that will drive you to it. So, I think there's an argument to be made that any civilization that builds that reaches our capacities, our energy harvesting capacities, is going to, the second law of thermodynamics demands that there's some feedback. There's no such thing as a civilization like this without feedback on its planet. So, there's an argument to be made that, you can't avoid climate change, which, if I might add, changes. When I deal with climate change denialists a lot through NPR and the other stuff I've done for the New York Times, and so often, like, what they want to do is get into an argument with you about, like, did we change the climate, right? That's the whole thing. You try and show them data, they don't really care. But what I love about this perspective is it completely flips the question. The question is not, did we change the climate? It's like, duh, what else did you expect to happen? We built a world-girdling civilization that uses a significant fraction of the biosphere's energy, or at least a fraction. What else did you expect? Like, how could there not have been an effect? So it kind of, this perspective, what I call the astrobiological perspective, really changes how we talk about climate change.
So are you saying that this specific kind of climate change is a pretty likely byproduct of civilization generically? And by this kind, I mean where, carbon dioxide is it is carbon dioxide, right? Carbon dioxide is the problem? Or do you just mean that you're going to be extracting and degrading energy on a large scale? You're probably going to be messing with the climate in some sense.
Yes, that's really the thing to understand. So that, we have risen to the capacities that we have by harvesting fossil fuels. We basically burn stuff, right? Before we had fossil fuels, we were burning biomass. But it turns out, if you do the work, you can see that pretty much any type of energy that you harvest, and if you're putting it to work, if you're using it for work, the second law of thermodynamics says, look, there's going to be waste. There's going to be feedback. There's going to be entropy generation. So, for example, some researchers did some work looking at if you tried to power this civilization by wind, if you maximally extracted wind from the global circulation, you would still have an impact. You'd have somewhere, what is an equivalent to, they said, around 2 degrees of climate change. So, I mean, that's one thing we have to understand, this new perspective. And what I'm arguing in the book is we have to understand there's no free lunch. Some kinds of energy impacts, some kind of energy's use will have lower impacts than others, but you're not going to be able to have a civilization like this and have it be impact free. So that changes entirely how we think about sustainability and where we're going. A mature civilization, one that can make it to sustainability, is one that's going to figure out how to think like a planet, as I like to say, to understand how those feedbacks occur.
Okay, so let's do step back and look at the growing reason to suspect that there may be alien civilizations out there. They have to do with the Drake equation, which you mentioned, right? And that was an early, just kind of pretty theoretical equation for estimating the number of civilizations out there, right? And I mean, it was like there were a number of variables. It's not like we had a good idea of what those variables were at the time, and some of them are still a little fuzzy. But why don't you talk about, like, first of all, who Drake was and what the basic structure of the equation was?
Yeah. Okay. So Frank Drake was a pretty interesting guy. He was, he was a radio astronomer when radio astronomy was still pretty new, and he got hired by down in the big radio observatory in West Virginia, and he arrives there, and he'd always had a long passion for the idea of other intelligences. He talks about, he had a big collection of the Oz books, and those kind of, affected him. So he gets down there and he sells his compatriots on the idea of, why don't we use this big radio ear to look for signals from another civilization? So he does the first ever targeted, systematic search for extraterrestrial signals from extraterrestrials. And it was a small search, like, 2 stars. But, that's what and he called it Project Ozma, after the princess of in the Oz stories. So he does that, and he's kind of waiting around to see. He doesn't find anything, of course, and then he's waiting around to see who's going to make fun of him because of it. And instead, he gets a call from the government, basically, that says, "Look, we're following what you're doing, and we'd like you to put together a workshop of a few people to talk about extraterrestrial communications." So there's about 9 people: Carl Sagan, the guy who who discovered photosynthesis, a small group. And so they were going to have a workshop, and what Frank Drake did is he came up with this equation as a way of organizing the discussions. right? So the equation basically was, the end result of the equation would be how many civilizations are there out there now that we could communicate with, which is what you want to know if you're going to do a search, right? If there's only one out of a billion stars, good luck, right?
Right.
So his equation, it wasn't, I mean, it's not an equation like E equals MC squared. It's not a law of physics. It was a way of basically parsing all the things we needed to know to get the answer, right? So it wasn't like we knew them. He just said, like, look, first we're going to have to know how many stars there are in the sky. Then we're going to have to know the fraction of those stars that have planets. Then we're going to have to know how many of those planets actually are in the right place for life to form, meaning liquid water on their surface. And then there was the fraction of planets that have life, the fraction of planets that develop intelligence, the fraction of planets that that intelligence goes on to form a civilization, and then finally the lifetime. This is a very important number, what I like to call the final factor, how long a civilization lasts.
And that's where the great filter could kick in. If civilizations tend to go up in smoke pretty soon, then the average life of a civilization is shorter, and that could account maybe for why we haven't heard from any of these people, or whatever they call themselves.
Yeah, exactly. So, and that final factor matters for us, right? Because if the average lifetime is, say, 300 years, we've only been a technological radio civilization. We've only been a radio communicating civilization for, less than 100. So if that lifetime is 200 years, 400 years, on average, we're in trouble, because it means in general nobody makes it, right? You have to be really lucky to make it beyond 200 years. If that average lifetime is 200,000 years, then it means, you can make a lot of mistakes and still make it through. So, that's why for us, this final factor, the average lifetime of civilizations, becomes so important. So Frank Drake, they have this meeting. They're pretty much guessing all the terms except the first one. The only one that was known at the time was the first term, which was
number of stars.
Number of stars, yeah. You can think of it as the number of stars in the galaxy. It's really the rate of star formation, but we don't need to worry about it.
And the whole thing, the analysis is confined to the galaxy. I guess expecting visitors from other galaxies is a bit much.
It's so far. I mean, the idea was that they focused on.
Way.
You can make it general. You can make it larger if you want, but they focused on the galaxy because that's the signals. The strength of the signals. If you go beyond the galaxy, it's going to start getting hard.
Okay.
So here's the important thing. Since 1961, when that conference happened or that workshop happened, we have now nailed 2 more of the numbers. Right. Nobody in 1961 knew whether there were any planets orbiting any stars. It could have been that planets were really rare and you needed a miracle to make them.
And was there really no strong grounds for suspicion one way or the other, or was it kind of widely suspected that there were a lot of planets and we understood why we couldn't yet detect them, or what?
Well, actually, what's interesting about this is that, over history, because this question goes all the way back to the Greeks, right? Mm-hmm. Over history, it's gone back and forth. And in the 1900s, at the turn of the last century, the conclusion had been they were very rare because people thought you needed 2 stars to pass each other and pull out some material in order to form, to get planets. And those kind of stellar near misses were so rare, they thought, that you would almost never form one. So it wasn't until, and that was the dominant view, until about 1950s, mid-50s, when people started thinking, no, you probably got a disk of gas forming around a star when the star formed, and the planets would form in that disk. So up until 10 years before that meeting, most people thought planets were going to be really rare.
Okay.
So, fast forward to 1996, and we discover our first planet orbiting another star. Like, that was an epic-making discovery. We discovered a Jupiter-sized planet orbiting very close to its star, very weird kind of orbit from what we would expect. Since then, since 1996, we now know, we put together the data, this amazing work, especially the Kepler satellite, which, looks for when a star passes a planet passes in front of its star to be able to make the detection. We now know that every star in the sky, every stinking star in the sky, not just in our galaxy, but probably everywhere, has at least one planet.
Really?
And more than that, we know. Yeah, that's what's amazing, right? When you look at the night, every one of those stars has probably a family of worlds. I find that mind-blowing.
That is amazing. And then the variable after sheer number of planets is how many, kind of in the Goldilocks zone or whatever. I mean.
Yeah, that's exactly it. So the Goldilocks zone. So the way we think about it is that we talk about the habitable zone, or the Goldilocks zone. And that's the range of orbits where you could like pour water on the surface of the planet and it would just sit there as water. It wouldn't, freeze, and it wouldn't just, boil away. So, if you're too close, obviously, your planet's too hot, it's going to boil away. If you're too far away, it's just going to freeze. So that habitable zone was the place everybody was interested in. And it now turns out that if you look at the sky and you count up 5 stars, one of them has a planet in the right place for life to form, is one planet in the habitable zone. So that's a lot of stinking planets in the right place for life to form. As a matter of fact, so this paper that my colleague Woody Sullivan and I wrote, we figured out, this wasn't a very hard calculation to do, how many planets that is in the universe, and that turns out to be 10 billion trillion planets in the right place for life to form. So that's
10
a lot
billion
of
trillion.
10 billion trillion. Carl Sagan would be proud.
So how many total zeros are we talking about there? Like 12 or something?
It's one with 22 zeros following it.
22. Okay.
And you got to think each one of those is an experiment. Each one of those is a play. First of all, the thing I want everyone to understand is every one of those planets, regardless of where it is a place. If it's a rocky planet, you could stand on it. You'd see mountains. You could probably, some of them are going to have oceans. There's going to be rain falling. I mean, every one of them. Certainly everyone in the
Well, there may be
zone.
rainfall. I mean, we know that we don't know that there's water on them, right? We know that if water were there, it would persist.
Right. And, again, with 10 billion trillion planets, there are going to be water. We know enough about.
There's going to be a little rain, yeah.
Got to be a little rain in everybody's.
Got to be a little rain in everyone's planet, It's the nature of things.
I'm sorry to let people know that.
So so then the second and third variables, I guess, have moved in the direction very decidedly of increasing the chances of civilizations. Now, then there's these subsequent variables that remain a little murky, and I want to talk about them. But first, I want to jump ahead and just ask you a question I've always wondered about. Is like, so. The idea is that, okay, if evolution gets started on some of these, it happens kind of, in our case, certainly it tended to lead to more complex forms of life and in some sense smarter ones. I mean, a jellyfish is smarter than a bacterium. And ultimately one smart enough to be self-conscious and moreover build the technology that could be the basis for a civilization that could communicate with you. And the thinking has always been that if you look at how fast technology is moving at where we are in technological evolution, it wouldn't take that much more to give you vastly greater powers than we have, right? I mean, a few hundred years from now, it's like, who knows? So, well, go ahead. You want to say something about that before I get to my big question?
Okay, so that, the rest of the terms, once we pass, so now all the terms having to do with astronomy are nailed, right? And that's huge, right? All the rest of the terms, unfortunately, we have very little constraints, right? So one part I want to talk about is just the fact that because of these other terms that we've learned, because of the astronomy terms, the fact that we've nailed those, and the fact that we've actually learned so much about climate and planets, now we can sort of bracket those other terms. We can put them all together, right? And we can at least set what we call the pessimism line. I can tell you how bad the probability, I can tell you what the probability per habitable zone planet has to be in order for us to be alone, in order for us to be the only time it's ever happened in the history of the universe. And those odds are 1 in 10 billion trillion, right? So why is that number important? So even ignoring, I don't know anything about the probability of forming life. I don't know anything about forming the probability of intelligence. But what I can do now that I know all these planets is I can at least tell you sort of how bad all of those, the product of all those has to be in order for us to be the only time it's happened. And it turns out to be a number so small that unless, as I like to put it, unless nature is perversely biased against forming, evolving technological civilizations, then it has happened before. Can't tell you how often it's happened before. I can't tell you if they're here now, but I can tell you that unless nature's various evolutionary processes turn out to give you less than 1 in 10 billion trillion, then we are not the first time this has happened.
So for example, to take a specific case, unless the chances of life getting started on one of these, in principle, hospitable planets, unless that chance is like 0.0000 blah blah blah, and the chance of evolution once started reaching a level of intelligence that can create technology is 0.0000 and so on. In other words, all of those, I mean, have to be like super low, or else some of them have to be super, super low. And
right.
So you kind of have to think that we're super, super. I mean, the way you could, I guess there's a certain version of this that's intuitive, like, unless we were super, super lucky, we're not alone. But this is like a rigorous version of that.
It's more rigorous. What we did is we used the actual data, right? So when my collaborator and I were doing this study, we were like, look, we've got all this Kepler data. We now have nailed all of the astronomy terms. It ought to be good for something when it comes to thinking about civilizations. And, we did the best we could do. But we could set what we called the pessimism line. Mm-hmm. And now why is this important? Because, there's a history of people talking about this. There's a history of people trying to estimate all of these different probabilities for life, et cetera. And what you find is, even people who were pessimists, who considered themselves to be pessimists, that if you look at their probabilities, what they came up with per planet, mm-hmm. it's way higher than what we came up, what our empirical data-driven number is. So, like, even the people who were, like, really hardcore pessimists turn out to be optimists now that we have data about it. Now, mm-hmm. we still can't, that's different from a detection, okay? But we can at least say now that nature has so many opportunities to run the experiment that it's got to really, really be biased against it. There has to be something in the law of physics and chemistry to really keep it from happening, in order for us to be the only time.
In fact, and here's a line from the book. You say, we can only be unique if the laws of the universe are strongly biased against life and intelligence. Now, when I read that in the book, I thought, well, not so fast. I mean, there definitely are a number of evolutionary biologists. I mean, they disagree on this question of how likely the evolution of intelligent life was. Some great ones think that the evolution of something as smart as us was actually very likely. Some great ones don't. But what you're saying is like, look, even if you accept, if you ask these people who are saying, no, it wasn't very likely, if you ask them, well, how likely is it? They'd go, I don't know, 1 in 10,000. You'd go, okay, that's plenty. I mean, given how many of these planets there are, there's a ton of life out there, if that's the number, and assuming some other numbers.
There's a really famous paper that was done by Brandon Carter, I believe it was, in 1982, where he suggested the hard step model. He said that, look, the evolution of life, the evolution of intelligence, requires a bunch of hard steps. Each one is unlikely. And he suggested there were 10 hard steps, like the evolution of sex, the evolution of oxygen-bearing photosynthesis, whatever. He had a list. And he calculated, based on that model, he was able to derive the probabilities, and he came up with he said the probability of forming intelligence is 1 in 10 to the 20, right? So we said 1 to the 20, 10 to the 20 minus 22. He said 1 to the 10 to the minus 20. So basically, and in his paper, he says, this is more than enough to show that there's no intelligence ever, anywhere. In fact, from our calculation, from the data, it would have happened 100 times. There are 100 civilizations in his super, mega, hyper pessimistic model. And now we know that, at least people now think there's not 10 hard steps, there's only 5 hard steps. Right. Which means that actually there would have been, 100,000 or 10 million species civilizations over the course of time. So what you're saying is exactly it. It's just like even people who think they're pessimistic, when you confront them with this number that comes out of the Kepler data, it turns out that they're not actually pessimists.
And the hard steps, by and large, are things thresholds that had to get crossed, and that, so far as we know, only happened once, I think, in most cases. There was a good book by John Maynard Smith and a guy with a Russian last name on this, and Maynard Smith was a great biologist, and they emphasized, I don't know how many they had, 5, 6, 7 or something, maybe it was 5, and he was pretty pessimistic. But again, you're right. I mean, first of all, people considered as great as him think it was extremely likely we'd have intelligent life. But even him, if you had said, well, what are the odds? I think he'd give you a number higher than what Brandon Carter gave you. Brandon Carter, he wasn't actually he isn't actually a biologist, is he? Or am I?
No, he's a physicist. Yeah, no, his argument was pretty brilliant, but it was based on this sort of just doing things that are very general. But yeah, so that's exactly it. So that's why that's why I'm going to argue that this meaning us and everything we're doing most likely has happened before, and all of those civilizations have had histories, and all of those civilizations, or many of them, will have triggered some version of climate change, and now we're at the point where we can actually do models of what the coupled evolution of a civilization and its planet should be, to try and at least come up with a theoretical value, right? A value based on models for what that average lifetime is. So that's the work that I talk about that in the book.
So that's what you call theoretical archaeology or something of exo-civilization?
Yeah, the theoretical archaeology of exo-civilizations. That's
are you the founder of this field?
I am the founder of the theoretical archaeology of...
If you go to enough trouble to come up with a term like that, you should definitely be hailed as the founder of the field. Theoretical archaeology of exo-civilization. Congratulations. So someday you could be you could occupy like a chair at some university, the Bob Wright Chair of Theoretical Archaeology of Exo-Civilization.
Are you going to endow a chair? That's great.
If I win the lottery...
Jack will get it started.
If I win the lottery, you are my guy. Don't worry. Okay, so before we get to the theoretical archaeology of exo-civilization, I'm going to get to this question I wanted to get to, which is, this is the why haven't we heard from them question, which I guess is what the term Fermi's paradox that's a question, Fermi's paradox. He's this great physicist who said, well, why haven't we heard from them if there are so many, basically?
Yeah.
It seems to me like one answer is, we're talking pretty long distances, right? And you can only transmit information at the speed of light. So like if you imagine that they got to, let's say that 300 years ago, they got to where we will be in 300 years, and that gives you vast powers to communicate across vast distances, well, you still are constrained by the speed of light. So they would still have to be within 600 light years of us in that scenario, I mean, right? Or do I have the math wrong? Anyway, you get the point.
No, the math is generally right. But the thing is, if it's happening a lot, you would think that, even if it's really happening a lot, then even species that don't last long, they're kind of popping up all the time. So we should still see signals from them.
And some would be way ahead of us. If it's happening a whole lot, some of them are thousands and thousands and tens and hundreds of thousands of years ahead of us.
Yeah, that's why I do not. When it comes to, there's different ways of thinking about the Fermi paradox, but the idea that the stars are silent, David Brin, who's a great science fiction writer and scientist, he came up with the idea of the great silence. I respect what he says, but in general, I don't agree with that idea, just because we've never done a comprehensive search. People think that, there's SETI scientists out there all the time scouring the sky. The truth is there's never been money to do SETI. So people have looked a little bit here, they've looked a little bit there. There's so much to look at, right? First of all, if you're just using radio, what wavelength of radio do you look at? When do you look? Which stars do you look at, right? Jill Tarter has said, she's compared the amount of studies that we've done to the amount of studies we need to do as sort of like there's an ocean and we have taken a thimble and dipped the thimble in the water. That's how much of the ocean we've looked at. And we're already saying oh my God, the stars are silent. So it's we just
so
have
the signals we could be awash in signals from alien civilizations right now and not know it?
Yeah, we just not know. We haven't done the search because also maybe radio, it's not radio. Maybe it's lasers that, we should be looking for. Maybe there's... So here's an interesting thing. When I talk about it, we have now entered a new era when it comes to SETI, to thinking about extraterrestrials. It's not your grandfather's SETI anymore, right? So we think of SETI as like taking a radio telescope and pointing it at a star. But we have to understand now that we found all these planets, and we're staring at all these planets. The next 30 years, we are going to be staring in detail at these planets, characterizing their atmosphere. When the planet passes in front of the star, there's a moment where the starlight passes through the atmosphere, and we can look at that light and tell what the atmosphere is made of. We've already just, found, I think, carbon dioxide or carbon monoxide in some planets. And as time gets on, we're going to be able to even tell, the hope is we'll be able to see the spectral signature of a biosphere, right? If you see oxygen in a planet's atmosphere, that will probably potentially tell you that there's a biosphere there, right? Because oxygen would react away very quickly unless you have weird circumstances. So we're going to be staring at all these planets anyway, that, we have to be prepared for the chance that we're just going to see something weird on that planet that may be evidence of what we call them technosignatures, right? People are getting geared up to look for biosignatures, but we may just stumble on a technosignature.
Which would be a sign that they've actually invented technology.
Right. It could be either like pollution in the atmosphere. It could be Avi Loeb from Harvard has proposed that if you're using a lot of solar panels, there'll actually be a spectral signature from the reflected light of the solar panels, of the silicon. So this field is just opening up, right? So we're just, with all these planets being discovered and our ability now to study them in detail, it's a whole new universe. No pun intended.
So to speak. So, but on the question of actual visitation, now that is unlikely, right? Because of course, we don't know how fast you'll be able to travel if you're 1,000 years ahead of us technologically. I guess in principle, the limit on that is also the speed of light. Is that?
It is the speed of light. Yeah. And I'm kind of a believer that it's going to be very hard to crack the speed of light. Maybe that's just a universal rule. I'm up for warp drive. Hey, warp drive sounds cool to me. But it's also entirely possible that, we're not going to be able to crack that. There is no way to crack that, in which case you're stuck with the speed of light, which means it'll take, it can take hundreds of years to get from one star to the other. So I take the speed of light pretty seriously. However, we just did a paper on this, right? Even if you traveled only at the 10th of the speed of light, if you had like a century ship, like you had this ship that you could put, human beings in and, have 1 or 2 generations or 4 generations, born and die in the ship, then one of the things about Fermi paradoxes that this guy Hart showed was that even if your ship was only traveling at a 10th of the speed of light, and every time you landed someplace, you built another ship and sent it out, then in just about 600,000 years or so, the whole galaxy will have been touched. Right? So 600,000 years seems like a long time, but from the galaxy is 10 billion years old. So that's a version of the Fermi's paradox that's a little bit harder to beat, right? If people are doing this, if civilizations are colonizing via these kinds of ships, then it is that front, that settlement front crosses the galaxy pretty short timescale.
Well, how far is it from where we are to the outer extremity of the galaxy from us?
The galaxy's, I think, oh my God, am I going to get this right? About 100,000 light years across. So from one end to the other.
That's not that much, actually.
It's not. So if you're willing to give yourself hundreds of thousands of years, and if
there could easily be a civilization 100,000 years ahead of us.
Right. So that's a little bit more harder to get around, and we just have a paper on that showing that actually. It's that settlement front is gonna propagate fast enough. It's hard to get around that. But here's the trick. Here's the thing. It may be that settling a world is very hard, right? It may be that there's not if you're an oxygen-breathing species, you may need an oxygen-bearing planet, right? You may need a planet that doesn't have microbes that are too different from yours, right? So this idea that you can just land anywhere and start a settlement, if you relax that, then it turns out that you can still have the galaxy be very settled, but the last time you were visited, right? The last time you were visited may have been 100 million years ago, in which case there's no evidence left over, right? So, I don't know if you saw this paper that Gavin Schmidt and I did, where we showed that, how would you know even if there was another civilization on Earth, a dinosaur civilization? Could you tell whether or not the dinosaurs had actually had a civilization? And the answer would be pretty hard because after just a few million years, all surface evidence is gone. So all you're left with is fossils, and most stuff doesn't get fossilized. And certainly a very short-lived civilization wouldn't be a whole lot of fossilization. So if aliens landed here and settled and lived had a civilization for 100,000 years, but it was 20 million years ago, there might not be any evidence left on the surface to see it.
So we're not ruling that out either. It's getting weirder and weirder. So one quick question.
It's getting weirder and weirder.
I'm surprised that, although you're willing to accept the speed of light as a speed limit, you're not, you're a little casual about it. I thought it was almost ironclad, and for example, with quantum entanglement, that if it turned out you could actually use entanglement to send information instantaneously, which you can't, but if you could, that would be mind-blowing, because Einstein would have been wrong or something. In fact, he thought, well, never mind. Anyway, right? So I thought everybody agreed that when it comes to actually transmitting information or physical stuff, speed of light is it. Don't get your hopes up.
It is. That's absolutely true. But when you can't, the idea of a warp drive, right? The idea that, so what Einstein gave us was the possibility to make wormholes, right? That the universe, you have 2 points that are separated by this much distance, but since space and time bend, you can try and bring them together, you hop across and then unbend them, right? So that's like the staple of science fiction. Warp drives bend space-time to be able to make distances shorter. Now, of course, there's no coherent, really, model for a warp drive. Well, that's not entirely true. But it would require energy, they call negative energy or negative pressure, which we don't even know really what that means in terms of like making it. So yeah, absolutely. The speed of light is constant. What I'm just saying is the speed of light is an absolute rule. I'm just saying that, like, who knows, maybe there will be a technological advance that allows you to make warp drives. But I tend to think it's going to be really hard, and it may not be possible. So that's why I think of it this way. Like, in 1950, what was the fastest a person could travel? An average person, maybe a few hundred miles per hour on a jet plane, right? 1960, say, right? What's the fastest speed you can travel now? A few 100 miles per hour on a jet plane, right? We've had almost 50 years, 60 years, and we haven't really been able to go any faster. So it may be that, all our dreams of, infinite technology, there may be real limits that you can't break.
Yeah, could be.
What that means is the solar system is the real future of humanity, right? The next few thousand years, the playground is going to be the solar system. We're going to try and settle Mars and develop real human habitation of Mars and, asteroids. We'll find every nook and cranny in the solar system to expand human civilization. So
you're on the Jeff Bezos bandwagon.
I'm a big fan of The Expanse. Have you watched The Expanse? Expanse, greatest show
My
ever.
wife is an Expanse junkie, and The Expanse, we should say, is on the Sci-Fi Channel. And I actually sent her your tweet. She was so gratified when you tweeted that it's a great work of science fiction, because she tried to get me interested in it. And I said, like, the first 2 episodes, maybe I'm getting old, but it's pretty hard to follow. And she said, it is, right? The first couple of episodes are.
You got to really stick with it because it's such an intertwined story, and they got to spend, there's like 5 different storylines that eventually will come together, but the first 4 or 5 episodes, they're laying the groundwork. So my recommendation.
I can tell I'd like it because it's kind of left wing in a way. At least it pays attention to issues of class and exploitation.
Oh my God. Yeah.
And also it's like one worldish. You've got the United Nations. In fact, you've got the United Nations per se, I think, is still a thing, right?
Yeah.
I'm going to give it a second shot. We got distracted by Wild Wild Country, or I did, so I'm going to give the Expanse another shot. But anyway, what were you saying about the Expanse?
Well, the point about the Expanse is what I love about it is it gives a fairly realistic picture of what humanity's future in the solar system would look like. The science is really nails important parts of the science. And that's what I think, it may be that interstellar travel is just ridiculously hard, and it may be very difficult to settle on other planets. So the solar system is really the playground for intelligent species. If you make it through climate change, which is a big deal in The Expanse, if you can make it through climate change, then what you get is your solar system, and that's where the next stage of the evolution of intelligence and civilization happens.
See, what I think is underrated as a threat to our making it through our collective teen years is just human conflict. Now, partly that's because to solve climate change, we're going to have to be getting along well enough to do the stuff we need to do. So too much conflict would contribute to that, the exacerbation of climate change. But there's also all these, new biological weapons and so on. So I think, all my progressive brethren spend almost all of their apocalyptic time thinking about climate change, and I'm lobbying that we devote some of our apocalyptic time to plain old-fashioned biblical apocalypse, people fighting, Well,
the thing about climate change is it's just going to make everything worse, right? It's not, as I say to people, because, so like I said, I deal with a lot of climate change denial, which is super frustrating. But the thing I always say is look, we can't tell exactly what's going to happen with climate change because prediction is hard. But the one thing we can be damn sure of is it's not going to make anything easier, right? And it could really be an existential crisis. So, but the thing about climate change and dealing with it, right, that's why the whole cosmic teenager thing really makes sense, because it's a lot of, here's the problem with climate change, right? It is such a fundamentally new encounter for human civilization that we just really don't have the evolutionary baggage to help us with it, right? And particularly, I'm very interested in mythologies and how mythologies have always helped civilizations make sense of themselves. And the thing about climate change is there is no mythology for it, right? It's a modern event that other than flood mythologies, we just don't have a story for it. And the only story we have really is we suck, right? Oh, human beings are a plague on the planet. We're terrible, And my whole point in the book is that, look, you got to give that up, right? Biospheres, some biospheres are going to generate civilizations. That's just, we are what the biosphere is doing now. A city is no less natural than a forest, right? Forests were once new evolutionary players on the planet. They came in, they changed the planet, then the biosphere moved on to the next thing. We are what the biosphere is doing now. An intelligent technological civilization is the biosphere's latest experiment. And, even if we drive climate change, even if we drive a mass extinction, the biosphere is just going to pick it up and use it for the next, to create some new niches for itself. But the problem is we won't survive it, right? So we have to be honest about when we're dealing with climate change, it's not about saving the planet. That's ridiculous. The planet, nothing we can throw at the planet is going to eliminate the biosphere. It's about saving the project of civilization and making sure that we're still part of what the biosphere is doing, 3,000 years from now. So really, this astrobiological perspective I'm arguing for gives us a new mythology. It gives us a conceptual framework to understand what's happening to us. It's not about Democrats versus Republicans or business interests versus environmentalists. It's about the biosphere running an experiment that, either we're going to make it through or we're not going to make it through.
Now, somewhat relevant to this is this guy Vernadsky. You talk about a lot of interesting people in the book, of course, Fermi and Drake and so on, and you get into Lynn Margulies and Lovelock and the Gaia hypothesis, but this guy Vernadsky, this Russian, I guess, did he come up with the term biosphere? But in any event, he also came up with the term noosphere, Noosphere, right, which is,
right.
And then that later was adopted by this theologian, Pierre Teilhard de Chardin, in an interesting way. But anyway, what did Vernadsky mean by the noosphere?
Yeah, so it was built off the idea first of the biosphere. So what he recognized, he was a biogeochemist. He was one of the first guys to recognize that in order to think about geology, you have to think about physics, right? And then he recognized in order to think about geology, you have to think about biology, because the life was a full player in the evolution of the planet, right? Life had hijacked the planet and completely changed its evolutionary pathway. And the easiest way to see that is to take a deep breath, right? There'd be no oxygen on the planet if it wasn't for the blue-green bacteria that generated, right? And that completely changed Earth's chemistry, right? Mm-hmm. So he developed the idea of the biosphere as being the sum total activity of the Earth and its co-evolution with the rest of the systems. And then after thinking about that for a while, he thought now we have human beings, and that thought, right? It was the output of our industrial activity, which is basically a manifestation of our thinking. That now we should think about the noosphere, the thought sphere, which had enveloped the planet. And Desjardins picked that up and made it kind of much more of kind of woo kind of idea. He was a Catholic.
He was a Christian theologian. He was a Jesuit. He was also a paleontologist, so he was something of a student of evolution.
Scientist too. And so his idea was that there was also a world spirit, right? That in some sense it was world soul. It wasn't just thought; it was the world soul, and that there would be this evolution to a higher plane. He had a more teleological view, but the Vernadsky idea was sort of the more grounded one. And because of Desjardins, people kind of poo-pooed the noosphere. But then it turned out that we kind of went out and built one by mistake, right? The internet,
right?
Right now I'm standing here, and there are literally radio waves of thought. There's information passing through my head right now. The world is enveloped in thought, and so the noosphere may be part of that. In order to develop a sustainable version of the biosphere, to have a biosphere with a technological civilization, a development of a noosphere may be an essential part of it.
Well, and what I like about the spiritual dimension that Teilhard de Chardin brought to it is it could be that, he saw it as like this suffusion of like brotherly love emerging as part of the noosphere. And of course, in his view, that was the fulfillment of Christianity's teleological, assertion. But what's interesting about that to me is that it could be that if we're going to pass through our teen years, we need to make a kind of a moral progress that you can call spiritual if you want, so far as I'm concerned. But the point is, if we don't become enlightened enough, in fact, you use the term, you describe Vernadsky's conception of noosphere as the planet, quote, waking up. Well, that also has these connotations of enlightenment in the Eastern sense. I mean, it could be that unless we reach a higher stage of wisdom, and a more sophisticated, actual practical moral system and so on, maybe we will be cast into the dust heap of history. So I kind of like I like that part of the noosphere.
Well, reaching back to your recent best-selling book, Why Buddhism is True, that's exactly it. We're both contemplative practitioners. And it is true that, in order to deal with climate change, we're going to have to sort of add some new evolutionary behavior. We're going to have to evolve, literally. We're literally going to have to evolve new collective behaviors in order to act together to deal with this. And I think in many ways that is going to require shedding some of the evolutionary baggage that we have, and that will require the development of wisdom. And so in the end, as I always like to say, you sustain what you value, right? And you value what you hold sacred, right? And so in that way, there is a spiritual or sacred quality to what you have to do in order to make this work for us, certainly. But, probably if you think of, compassion as being, and the identification with life as being things that are sacred, then that's exactly what it's going to require to make this transition. The problem for us is that we thought we were different from the biosphere, right? Like that we could do whatever we want. We could drink lots of water bottles and throw them away, and it wouldn't have any effect. We thought we were not part of the biosphere. The whole lesson of climate change and the Anthropocene, right, this human-dominated era we've entered in, is that we're part of the biosphere. Like we are we can't escape from it. We can't step outside of it. So in some as yet unimagined way, we're going to have to come into some kind of cooperative relationship with the rest of the biosphere. That's probably what a sustainable version of any planet looks like. The civilization has figured out how biospheres work, and it's, as I like to say, it made all boats rise. The whole biosphere becomes more productive, so we become more productive too. And that is going to require an identification with life. It's going to require some kind of compassion for wise action, right action. So yeah, I think actually in the end, there's going to be something about the spirit, and about the human spirit that this is going to call to.
Mm-hmm. So before we turn to the theoretical archaeology of exo-civilization, I wanted to ask about this Gaia thing. I mean, back, in the 80s, the Gaia hypothesis was a big thing. You had Lynn Margulies, who, by the way, made other very important contributions. I mean, I think she figured out the evolution of the eukaryotic cell pretty much in a way that's held up, I think. The argument...
Yeah, and she developed cooperation. She was the one who introduced cooperation as being as important as competition in evolution.
And the idea that the complex cell, and that's one of the thresholds life has to pass through, the transition from the simple cell to the complex cell with a distinct nucleus and everything, she posited had come through symbiosis of initially discrete cells had kind of done a merger, and I think that's actually held up. So anyway,
it has. The mitochondria, I think that's it. The mitochondria were one of the organelles that was separate and free living, and then became part of the symbiosis.
And then, but then separate from that, she got into this Gaia thing, and James Lovelock was another advocate, and that was controversial, and people said no, that's teleological. But I think you think there's something of value that remains from that concept. Why don't you tell us a little bit about what the Gaia hypothesis is, what the idea of Gaia is, and what there is that you think is of value?
Yeah, well, actually, it turned out for the community there was a huge amount of value. So it was Lovelock who really first proposed the idea. He came up with the idea. This is the amazing thing: sitting in the same office that Carl Sagan had at the Jet Propulsion Laboratory. Carl Sagan just pops up in this story all over the place. But what he recognized was that, he was
Lynn Margulies' husband for a while, right?
And he was Lynn Margulies'.
I mean, let's go ahead.
Yeah, the only reason why Lynn Margulis got involved in this is because Lynn Margulis was trying to think about how microbes could have changed the atmosphere, and Carl Sagan, who wasn't really a big fan of Gaia, said, "Oh, you should talk to Jim Lovelock."
Yeah.
So the Gaia hypothesis they came up with together was that basically life hijacks planets, and then through feedback loops can keep a planet can keep the planet's conditions, can modify the planetary conditions to keep it good for, hospitable for life over very long timescales. And so people really, in the beginning, attacked that and it wasn't really their fault so much. It was just that it became this sort of using Gaia, giving it the term Gaia was one of the reasons.
Gaia was a goddess or something? What was it?
Gaia is the Greek goddess of the earth. And it was actually Lovelock's friend, the guy who wrote The Lord of the Flies, Goldsmith, Golden, yeah, who actually suggested that. They were walking one day, and he said, call it Gaia. So it became this sort of new age, groovy idea. But really, what they meant was just that there were feedback loops that could, that life could control. Like if the temperature got too high, more microbes of a certain kind would start to produce, which would produce more, chemicals, which would lower the temperature. But so what people got angry about was the idea life wants this to happen. There was some teleology. And they were like, no, this is all blind evolution. And so what happened is eventually people dumped the name Gaia, but it became what was what was called Earth systems theory. And that is the way everybody thinks about, climate change. All the Earth scientists now think in terms of Earth systems theory. So really, Lovelock and Margulis won the debate in the most important sense.
Can I just drill down? So an example would be like if the amount of oxygen, if plants become so profuse that the amount of oxygen increases and animals get so profuse that the amount of oxygen increases to the point where plants are having trouble breathing, then there is a feedback mechanism that, as a matter of fact, solves that problem.
That will bring the oxygen levels down. Yeah, right. You'll generate more, oxygen-eating things, and so there's a bunch of different feedback loops that people
keep things at a kind of equilibrium. And the controversy, the point made by the initial critics of Gaia was, well, okay, it works like that, but it wasn't designed to work like that.
Exactly.
The planet as a whole isn't a product of natural selection. Okay.
Right. Exactly. There's no consciousness for the planet, for the biosphere. But here's the interesting thing, and this is the point I make in the book, is that once you have a intelligent species there, which is trying to develop a sustainable version of itself, now suddenly there is purpose, right? In order for us to develop a sustainable version of our civilization, we're going to have to sort of interact with the biosphere, do things that will become the mindfulness. We will become the way in which the planet wakes up. And that's probably generic, right? So for other civilizations as well. So in some sense, once a biosphere develops a technological civilization, in order for it to survive, it becomes the completion of Gaia. It becomes the mechanism by which the planet wakes up and does add teleology to the biosphere's evolution.
In the sense that the welfare of the planet is now being purposefully tended to, in the sense that we mean to do it, even if it wasn't purposeful before we showed up.
Right. It wasn't purposeful beforehand. It was a bunch of interacting feedback loops. There was no purpose in it. But once a civilization like us emerges, now there is intention, right? And that's interesting because now, especially if you're a long-lived civilization, you have now taken sort of stewardship, or you are the mind of the planet in some, very real way.
Yeah, no, it increasingly seems kind of like a superorganism. It doesn't. The internet seems like a giant global brain, but on the other hand, when you look at the political level and how nations are relating to each other and ethnicities are relating to each other, it doesn't yet have the harmony we associate with a superorganism, and that may be the challenge.
Yeah, right, exactly. That's the evolutionary part, that we're kind of we're kind of we've developed a psychotic noosphere, right? We have the beginnings of a global brain, and it's insane, right?
Yeah. Good news, bad news joke. Okay, so now it's time to tell us when Jeff Bezos does endow the chair of theoretical archaeology of exo-civilization at the University of Rochester, and you're like sitting on the chair, and people are giving you like full body massages, whatever you get as a perk. What are you going to describe? What exactly you'll be doing?
Okay, so we actually have a new paper which has come out already just very recently, where we took the first step at that. And so obviously, well, it's theoretical because all we can do is use the laws that we know to map out what could happen, right? So what we've done is we've taken a first step by writing down equations that will describe the coupled interaction between a planet and its systems and a civilization, right? And so how do we do that? Well, the planet is going to provide energy resources, whatever it's going to be, fossil fuel, solar, whatever. The population is going to use those resources, and by using those resources, it's going to increase its capacities. And what that's going to really mean is it's going to have more babies, right? The population is going to increase the more energy it gets to harvest, right? That's exactly why we would not have 7 billion people on the planet if it wasn't for fossil fuels, right? But of course, by using that energy, you're also now going to feed back on the planet, right? So the planetary state, think of it as the temperature. The temperature is going to start changing because you're using the resources to generate more babies, more energy, more feedback, more temperature. And at some point, if the temperature gets too high, now your ability to have your civilization work function is going to diminish. Like you imagine if large-scale agriculture becomes really hard to handle, then your numbers are going to drop, right? So the state of the population and the state of the planet are coupled. So what we did is we ran these models and looked at what the histories were. What was the average kind of history? And we saw 3 basic kinds of history. One was a nice smooth landing. The population rose, the temperature of the planet increased, but you came to a nice steady state where everybody now stayed steady. We also saw die-offs where the population overshot the carrying capacity of the planet and came crashing down. Maybe 70% of the population died from its peak, but then you reached a nice steady state. And then the worst was the collapse, where the population skyrocketed, the temperature skyrocketed, and the population went all the way down to extinction. So that was a first step in the theoretical archaeology of civilizations. And what we want to do now in the future, what I'll be doing when I have my beautiful chair and getting my back rubs, is that we'll start making those models more realistic, putting in real climate models, putting in actual numbers for how different kinds of energy resources feed back on planets. So we'll make the models more realistic to try. And in the end, what we're going to get is a theoretical value for that average lifetime of a civilization, right? We'll run thousands and thousands and thousands of models with all different kinds of conditions, planets that are close to the star, planets that are further from the star, planets that have lots of oxygen in their atmosphere, civilizations that start off using fossil fuels and switch to solar. And in the end, we'll get, at least when it relative to climate change, we'll get an average age for the civilizations.
And did doing this make you either more or less pessimistic about our own chances than you had been?
No, well, actually, the good news was there were steady states. There was sustainable trajectories. They're in there. The models, the great thing about running these models, as opposed to just yelling at each other in an argument, is that the models have their own logic, right? Once you crank up the math, the models are going to, all these interactions are going to occur that the different kinds of physics and biological interactions, and the models will tell you what stories are hiding in there. And so it was great to find out that one of the stories hiding in there was sustainability, but at the same time, there were other worrisome, outcomes where, like, for example, we modeled if a civilization switched from a high impact to a low impact resource, like fossil fuels to solar. And what you'd get is when you switched, it looked like things were getting better. Your population's going up, your planet's heating up, and then it would kind of level off, and then boom, it would still collapse, right? So those ones, the civilization made the right choice, but it was too late, and they still collapsed. So, there was a pretty rich set of behaviors hiding in there.
So the sooner enlightenment dawns, the better. We can agree on that.
Yes, we can agree on that.
So, final question. So when you think of, the universe, it's like, we've all, sat there occasionally and looked out and seen the stars. Do you actually but I never think of there being beings out there. I just think of there being stars. I'm imagining this vast expanse of quiet. I'm not imagining somebody going to a convenience store 7,000 light years away. Yeah. Is it part of your imagination of the universe that the convenience store is? You're nodding your head.
Convenience stores. But, I look out at the stars at night and I'm so pissed off. Because there's all these worlds out there. There are all these places, and I'm never going to get to see them. So, I just, I feel, in my gut, I feel like the universe is this incredibly rich, varied set of possibilities, and some of them are just life, and some of them are intelligent life. And yeah, I kind of feel like the universe is teeming with innovation, and I'm stuck on this damn rock. Now, it's a nice rock. I like the rock.
Nice rock. Nice endowed chair.
Yeah.
Theoretical archaeology of exo-civilizations.
Nice rock.
So, you could, first world problems.
Let's not screw it up.
Okay. So the book is Light of the Stars, Alien Worlds and the Fate of the Earth by Adam Frank. It comes out even as we speak, because you and I are actually taping this a week or two before pub date, but we're gonna post it at the very moment of publication.
It'll be good. Yeah. So June 12th, it's coming out. It's it was doing the research and writing the book really took me to new and fascinating places. And it was actually a great joy. In terms of where. Yeah, because where it took. I was doing research. It's based on a bunch of papers I wrote, but it's also I had to learn all these histories, and it showed, for example, photosynthesis. When I recognized what oxygen-based photosynthesis or oxygen-producing photosynthesis, how it had changed the world, how it had literally had recast the whole evolution of the Earth. I mean, that was a week where I was just walking around stoned, with that realization. So, it was a joy to do that.
Well, it shows. It's a fun read, and your enthusiasm definitely comes through.
Good.
So thank you, Adam. And
thank you, Bob.
This is, I think, the third conversation we've had here. Let's have another one down the road.
Absolutely.
All right. Take care.
Take care.